Okay, so 2-5, starting your proofs. Yippee, yippee, skippy. Some important things. Well, first of all, circle an equation. There's only one of those things there that's an equation. What's the only thing that has an equal sign? This is the only one that counts as an equation. This is an inequality. These two are expressions. So an equation has an equal sign. And then we're not going to do 2 and 3 today because we're short on time. But today's definition is justify. And that's what we're going to end up doing in our proofs is justify. So to justify a step in a solution is to provide a mathematical reason why the step is correct. And those are your postulates and theorems. And definitions can be used as well to justify things. One of the things that you must become aware of are your properties of equality. So before we do the usual vocabulary part, because depending upon who you had for algebra depends upon whether or not you're given it. So flip this over. Let's talk about the properties of equality. And you need to study these. If I were you, I would put each one of these on a flashcard and start to study what happens to the left side and the right side. So let's just start up here. In the middle, it moves out. So in the middle, we've got properties of equality. So let's start here actually with addition. So if you start off with A equals B, and the difference between this left side A and this side A plus C is what? What do we do to the left side? To go from A to A plus C. You added C. I'm trying to teach you to look at this because when you go through a proof, especially an algebraic proof, you have to know what happened to the left side from top down to see what happened. So over here, if I added C on the left, wouldn't I add C on the right? And that's your addition property of equality. Then let's move up here. If A equals B, there's two different numbers, but they're equal, they're two different values. On the left side, I have A minus C. What happened from A to A minus C? We subtracted. So on the right side, we must subtract C also to maintain that equality. Substitution just means if A equals B, then B can replace any A in any equation. So anytime you see an equal value being substituted for something else, that will count as substitution. And we've explored that a little bit. So substitution, property of equality. So for multiplication, we start again with A equals B, but this time we're multiplying both sides by what? C. Division, we're dividing both sides by C. What can C not equal? In a denominator? 0. So there's a little bit of a restriction on that. Then we have these three properties down here, which we'll explore a little further as we get along. The transitive property, which I said was law of syllogism. So you might want to put this on your flashcard, but this is your law of syllogism. Law of syllogism follows a transitive property. And I like to usually write it vertically to itself rather than horizontally out like it is here. It has if A equals B, and then notice the next one starts with what the first one ended with, and B equals C, then A equals what? C, because you take away what's repeated and put together the other two. So take those away, put those two together. So usually it looks like this. If A equals B, and B equals C, then A equals C. We just took out what they had in common and put those two together. So usually if you have three things, if and then, usually not always it is the transitive property. If it doesn't fall in this order, if it says A equals B, C equals B, so in other words the C comes first, this is reversed, and you can still have A equals C, that's substitution. So back up here for substitution, you could also have if A equals B, and C equals B, then A equals C, because they both equal B, so that means they both must be equal to each other. That's substitution. It's similar to transitive, but it's not in the correct order. It has to follow in that pattern for it to be transitive. And then we have symmetric. Symmetric just means we flip-flop the left and the right side of the equal sign. So if A equals B, then B equals A. Symmetry, symmetric. Reflexive means that A equals A. The left side looks exactly like the right side. Oftentimes we use this in a geometric proof to hit you upside the head. Remember that this thing equals itself. And typically from that point, when we use that, we will use it to substitute it in someplace. Because we're saying, remember, this thing equals itself, and then we're going to use that to substitute it. You'll see that today. So now let's go back. We're going to have this one in mind. Let's go back and look here at what's happening down below. So if you've got 3 plus 7, look what happens from the left to the right. And then we got 7 plus 3. Things are flip-flopping. Things are moving around. These properties are not, associative and commutative are not on there. So associative and commutative mean two different things. You might want to add this over here. Associative just means that you are regrouping. So you could have A plus B plus C, and then A plus B plus C on the other side, but maybe you group the A and B together on the left, but on the right side you group the B and the C together. So that's what regrouping. The same thing occurs with multiplication. A, B, C equals A, B, C. You might multiply the first two together first, and then multiply by C, or you could multiply the last two together first and then multiply by A. It doesn't matter what order you multiply or what order you add in. You're going to get the same answer. So that's your associative property. Commutative. Commutative's root word is commute. Doesn't commute mean to go from one place to another? So commute really means to move places. So you might have A plus B on one side, and then you just switch them around, B plus A on the other side. If I add 2 plus 3, it's not the same as adding 3 plus 2. It doesn't matter the order in which I add them. Same thing with multiplication. I could have AB versus BA. The root word of associative is associate. And girls do this all the time. We reassociate with friends. We change groups of friends all the time because we get mad at our friends. So think of associate as regrouping, commutative as moving. So what's this one? Is it associative or commutative? Are we regrouping or switching places? Switching places. And so switching places, isn't that commutative? And since it's addition, we're going to match this one to that one. And I would make flashcards of these ones as well. And I would put these examples on there. I'd put these examples as well as the specific number examples because this is going to make more sense to you. 12 times 4 equals 4 times 12. Are we regrouping or are we switching places? Switching places. So again, it's commutative, but this time it's with multiplication. So then these two must be associative. Notice that the 2, the 5, and the x, the 2, the 5, and the x stay in the same place. The only thing that occurs is two different things are grouped on one side versus the other. So this is the associative property of multiplication because we're using multiplication. And then the 1, the 9, and the 53, the 1, the 9, and the 53 have not changed places. They've just changed groupings. And so this is your associative property of addition. So add those to your flashcards along with these. All right, so then let's look at the distributive property, which is your final one that we're going to use. You all should be familiar with this. All we're doing is taking what's outside of parentheses and multiplying it to what's inside, whether it's a sum or a difference. So here they're just torn apart 24. Wouldn't 24 be 20 plus 4? And then we're going to multiply 5 times 20, which is, I have to write that down, 5 times 4. So 5 times 20 is 100. 5 times 4 is 20. And you get 120. And we do the same thing with subtraction, but we're not going to finish that one up. All right, so this one we're going to actually do a proof for this one. But let's start off with what they've given you. So they've given you a given and a picture. They may or may not give you a picture, but you should always draw a picture if you can. So they said that ray AB bisects angle RAN. The fact that they told you that I have a ray bisecting an angle, what's your conclusion about what that thing's called? Really loudly. What's a ray bisecting angle called? An angle bisector. What do we know about an angle bisector? Because that's what they're trying to get you to do down here. The minute we look at that given, there should be some information that we can conclude from that. So there should be no heads on desks, no leaning on desks. We sit up straight. It is rude to sit there and sleep on your desk when I'm lecturing. I took the time to come to work today and teach you. You're going to take the time and learn. It's a free education. You should appreciate it. Perhaps if you paid for your education, you might appreciate it more. All right, so what do you conclude from an angle bisector? That's one thing. It cuts the angles in half, which then means what about those angles? They are congruent. And what do we know about congruent angles? They have the same measure. So there's your if this, then that reasoning following through. So all of that came from this one little statement. So do we conclude that angle RAB is obtuse from that information? Yes or no? Nope. Do we conclude that angle RAB, here's RAB, is, what's that mean? Congruent to NAB. Is that what we conclude? Yes, so this is a possibility, right? Let's look at this one. NAB is congruent to angle RAN. Is that true? No, because that's the whole baby. So this is the one that we're going to conclude from that. So directly from this, I'm going to make the conclusion that angle RAB is congruent to angle NAB. This is called pre-proof planning. So that's something that you should have gotten no matter what. So then let's look at the proof. When you first do proofs, I'm going to walk you through it on a test. So you'll be given all the steps and you have to give all the justifications. Or you'll be given all the justifications and you have to give the steps. Or you might be given some and the other. I can tell you on your test that it is a multiple choice question. And then but you have to choose the answer choice that has everything correctly. And there's also another question where you do fill in something like this, which is extra credit. Okay? So the proof on the test is not difficult in the sense that you don't have to do it all by yourself. You've got 2 proofs today that you have to do all by yourself. So let's start through this one. So ray AB bisects angle RAN. So the first thing I would do would be to draw a picture if they didn't give me one. So I'm going to be drawing a picture. It's bisecting angle RAN. And the bisector is AB. So I know that B is on that ray. And I know that that's what my picture looks like. And I'm going to put congruence arc marks in there to remind myself of that. 100% of the time, your very first statement, this should be split into a T-chart that looks like this. Statements and reasons. So it's a 2-column table. Statements and reasons. 100% of the time, when you do your homework, I want you to write out the given, write out the picture, and write out the proof. They didn't tell you what the proof was, but we'll get to it here in a minute, because we're going to actually solve it. So 100% of the time, the very first statement is your given. So this is statement 1, reason 1. So statements get numbered and or lettered. So make sure you write that in. Then from here, we concluded that RAB was congruent to, they said NAB, you could say BAN, didn't you? Does it matter? Nope, they're the same thing. So I'll probably say BAN. Why? Because we were using the definition of an angle bisector. Now, I personally am going to make you write that out. An angle bisector cuts an angle into two congruent angles. That's what I want you to write out. Something to that effect. You don't have to, regurgitate the exact definition, but you have to get the definition out correctly in your own words. Then from here, notice the change from the left side to the left side. What's the only difference from here to here? It's a change in notation. So remember when you said that we had congruent angles, I asked you what does that mean, and what did you tell me? It had the same what? Measure. Remember this notation? We don't see it often lately, but it means the measure of angle RAB is equal to the measure of angle BAN. So this is statement 3. And anytime we have a change in notation, then you can just say, in this case, congruence of angles have equal measure. So that's a new one for you. You might want to learn that. If we're dealing with segments, you would say congruent segments have equal measure. Then from here to here, we have x equals. We'll go back to the original picture. Where did that original picture go? Go back to the original picture here. Didn't they say that this was x and this was 2x minus 75? Right? So here's where they're getting the x. Angle RAB, we are replacing it with an x. And angle BAN, we are replacing it with its value, which is 2x minus 75. When I replace something, isn't that substitution? The reasons always go based upon what happened above. So from here to here, I substituted. Right? So from here to here, I substituted. Then from here to here, what happened? I only see the left side. What happened from x to 0? How do you get 0 on this side? What must we have done? Subtracted x. If you were to solve this, you could subtract x from both sides to solve, couldn't you? In geometric proofs, we don't actually show the work. We just show the result of the work. So this is statement 5. Notice that over here we have the subtraction property of equality because we must have subtracted x from here. If I subtract x from here, what do I get? X minus 75. And so this is reason number 5. Then our next reason, our last reason, is we must use addition property of equality. So how do we go from 0 to 75? We had to have added 75. So if I add 75 to this side, don't I get x? So what they don't tell you is our prove statement must be here, prove. They didn't give you this part. X is equal to 75. They have to give you a given and a prove statement. They didn't give you the prove part because we're just solving it. But your last statement should be your prove statement. And technically, I would probably have a last statement here, statement 7, that said x is equal to 75. Because if my prove statement says prove that x is equal to 75, it better look exactly like x equals 75. So what property do you switch the left and right side of the equation? Look at that list. What property switches the left and right side? The symmetric property of equality. So this flow chart is going to be your best friend today. You're going to use a lot of this today. All right, so then let's go back and look at reflexive, symmetric, and transitive again. So these are properties of congruency, not of equality. They always deal with congruent angles or congruent segments. Segment AB is congruent to segment AB. Angle A is congruent to angle A. These are just examples of the reflexive property. Typically, as I said, we hit you upside the head by saying, remember, these are equal, and then usually what follows this is a substitution reason. So you might want to write that down. Symmetric, basically this would be your first statement, this would be your second statement. You just flip around the left and the right side, and that's what we did up here. First statement, the second statement, symmetric property. Same thing with angles. And then transitive requires 3 statements to get to the conclusion. This would be statement 1, this would be statement 2, and this would be statement 3. There would be various reasons for that, but the final reason on this third statement would be the transitive property of congruent segments, or the transitive property of congruent angles. And we're not going to do this part. Alright, so let's write a 2-column proof. So here you go. They've given you your statements here and your reasons. You need to put in a T-chart. So look what they gave you, look to see what you have to prove, and then there's a picture that goes with it. So they said that AB is congruent to segment CD. So this segment is congruent to this segment. Your job, and they've even put tick marks in there to tell you so. Your job is to prove that segment AC, this segment here, is congruent to this segment here. Here's a problem you're going to run into. You're like, well, yeah, I know it is. I can see it is. It's not about seeing, it's about proving. They overlap each other, don't they? How do they overlap each other? What segment is overlapping with them? BC. Okay? So look at what happens with our reasons. So segment AB is congruent to segment CD. Where did we get that? It was given. So 100% of the time, that first reason had better be given. Then I have to figure out a way to go from here to here. You will develop some pre-proof planning abilities. If I want to prove that AC is congruent to BD, isn't AC made up of AB plus BC? And isn't BD made up of BC plus CD? And if this is congruent to this, and this is congruent to itself, we were told already that that's congruent. So we're going to use some of that in here. We have to go from here to getting to that whole big piece. So somehow I have to get B plus BC in order to get to the whole piece of AC. Somehow I have to go from AB to AB plus BC so I can get to AC. I can't just go from here to here to AC. So look at how they do it. What happened from here to here? Isn't it a change in notation? What does nothing above here mean? What's that notation mean? How do you read that? I read this as the segment AB is congruent to segment CD. How do you read this? The measure from A to B is equal to the measure from C to D. That's no different than what happened up here, right? From here to here. Wasn't that congruent angles have equal measure? So what do you think we're going to say here? Congruent segments have equal measure. You're not going to get good at this until you start to study your proofs. You should be writing down. Okay, you're going to fail the proofs, and it's going to fail your grade in this class. So you got to learn them because they don't ever go away. So ignoring them is not going to make them go away. So you may not like them, but you better sit here and write it. If I'm writing it, so are you. Yes?
Do we always have the statements given to us?
No.
Or do you have the same amount?
Someday you will only be given this, and you have to come up with everything on your own.
So it's not when you give an amount, you have to have just every.
Correct. So you are, and in fact, there's 2 problems on your homework tonight that you're given nothing but this, and you have to come out with everything. So you have to look at other proofs and say, okay, how do they do this proof? I'm going to try to do mine the same way. And so you've got to study your proofs and try to make, okay, this proof's like that proof, and try to see some similarities going through there. Then from here to here, there's absolutely no correlation. BC is the distance from B to C is exactly equal to the distance from B to C. This is an equality property. Same thing equals the same thing. What is that? The reflexive, it's mirror image, a reflection, mirror image. So this is the reflexive property of equality. You can abbreviate it that way. And remember I said they're going to hit you upside the head with this saying, remember, BC equals itself. Typically, what follows is substitution. So look at from here to here. we went from AB to AB plus BC. Didn't we just take this and put it onto the left side? We added it. Then we add this right here. This went to here, and this went to here. Correct? So this isn't necessarily a substitution. Aren't we adding the same value to both sides? True or false? I'm adding the same thing to both sides. What property is that? Adding the same thing to both sides is not the addition property of equality. They're hitting you upside the head saying, I'm going to take the same thing that equals the same thing and add it to both sides. So this time we didn't use substitution. Then what happened from here to here? How do we go from AB plus BC got us AC? BC plus CD got us to BD. AB plus BC equals AC. Small plus small equals whole. Way back from August. Isn't that the segment addition postulate? Remember those things on flashcards you're supposed to be studying every day? This is why we study them, so that they can pop out in our head. So this is your segment addition postulate here and here. Segment, and they can do that with angles as well. So that's your segment addition postulate. Then what happened from here to here? It's a change in notation, isn't it? So don't we say that segments, we're going to say the converse of this. Segments with equal measure, whoops, no E there, with equal measure are congruent. Segments with equal measure are congruent. And that almost concludes our notes. So we'll finish our notes tomorrow. Start on your homework. You won't necessarily be able to finish it, but you better start it. If you don't start it, you're not going to have questions tomorrow, and you're going to be sad, sorry people.